You clicked because you want to run powerful AI on your own laptop without buying a server farm or paying cloud fees every time you generate an image. The hard truth is that for years, the industry told us this was impossible unless we had thousands of dollars in graphics cards and massive electricity bills. That belief has just been shattered by a new project called 1-bit Bonsai, which proves that extreme compression can turn your consumer hardware into a high-fidelity AI engine. By the end of this video, you will understand exactly how compressing a model to under 600 megabytes changes everything about what local artificial intelligence means for your workflow and why this shift matters more than any new release from big tech in years. For decades, the barrier to running large language models or image generators locally was simple physics. The math required too much memory bandwidth and storage space that standard laptops simply could not provide without overheating or draining batteries instantly. We were told that if you wanted intelligence density equivalent to a server-grade setup, you needed floating-point 16-bit precision, which meant gigabytes of model weights sitting in your RAM. This created a false dichotomy where developers had to choose between privacy and speed on one side versus cloud dependency and latency costs on the other. The 1-bit Bonsai project fundamentally breaks this trade-off by demonstrating that we do not need full precision to maintain high utility or creative output quality. The core innovation lies in how aggressively they quantize the model weights. While traditional models might store every number as a standard floating point value, Bonsai compresses those same parameters down to just 1 bit per weight, or roughly 1.58 bits using ternary formats. This is not a lossy compression that throws away data randomly. It is an intelligent pruning of redundancy where the model learns which numbers are essential for reasoning and image generation versus which ones can be discarded without losing semantic meaning. The result is a 4 billion parameter model that shrinks to just 572 megabytes on disk, representing a 14-fold reduction in size compared to full precision equivalents, while still retaining high-fidelity generation capabilities. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand why this matters for your daily workflow, consider the energy implications of running these models today. A standard floating-point 16-bit version of a similar model would consume 4 times more power during inference operations than its 1-bit counterpart. That means you are not just saving storage space, but also reducing thermal output and extending battery life on mobile devices significantly. The architecture supports direct integration with llama.cpp, which allows for zero configuration deployment across different operating systems without needing complex cloud setups or proprietary software stacks that lock you into a specific vendor ecosystem. When we look at real-world performance benchmarks, the numbers tell a story of dramatic acceleration rather than just size reduction. On an M4 Pro Apple Silicon chip, this 1-bit Bonsai model processes 131 tokens per second during inference tasks. If you have access to high-end desktop hardware like an RTX 4090 graphics card, that throughput jumps to 368 tokens per second. More importantly, the latency has been reduced by 78 times compared to legacy setups running larger models on similar consumer-grade silicon. This is not a marginal improvement. It is a fundamental shift in how fast you can interact with these systems, from inputting your prompt to seeing the final generated output appear. However, achieving this level of efficiency comes with specific technical trade-offs that every engineer needs to understand before deploying this into production environments. The 1.58-bit format requires a group size of 128 for optimal speed calculations during matrix multiplications. If you do not configure your backend correctly, the performance gains evaporate quickly because the hardware cannot process the data efficiently without those specific grouping parameters aligned with its architecture. Furthermore, while the model is designed to be backend agnostic, supporting Metal on Apple Silicon as well as CUDA and Vulkan on Linux or Windows systems, the actual speed varies significantly depending on which underlying engine you choose for your inference pipeline. This brings us to a critical realization about the current state of local AI deployment that most tutorials ignore completely. The shift to 1-bit models enables a new class of edge-native applications where the primary constraint is no longer model size or energy consumption, but rather the specific backend optimization required to sustain real-time interaction on resource-constrained devices. Community benchmarks show that high-end desktop GPUs like an RTX 308 can handle 8 billion parameter versions at nearly 5,000 tokens per second. Yet laptop-grade mobile chips face significant throughput constraints even with this compression technology. This indicates that while running locally is now feasible for almost anyone, the performance you experience will strictly depend on your specific silicon tier and how well it supports the chosen inference backend. The most valuable insight here concerns what we are actually measuring when we benchmark these systems today. Current data focuses heavily on throughput metrics like tokens per second or raw model size in megabytes, rather than providing a rigorous analysis of capability degradation compared to full precision counterparts. There is still a knowledge gap regarding the specific output quality of this 4B model versus larger architectures trained with higher precision, especially when running on edge devices like Jetson Orin, where independent comparisons remain experimental. We are seeing directional signals that suggest high utility remains intact despite aggressive pruning, but we lack detailed comparative studies that quantify exactly how much creative fidelity is lost or preserved in these compressed formats. As you move forward building your own applications or experimenting with local inference engines, remember that the definition of what runs locally has expanded beyond just hardware specifications to include algorithmic efficiency and backend compatibility. The technology proves that aggressive quantization does not necessitate a proportional drop in utility for consumer-grade hardware when implemented correctly. You are no longer limited by the physics of floating-point arithmetic, but rather by your ability to configure the inference pipeline to leverage these compressed weights effectively across different backends like MLX or llama.cpp. This shift fundamentally changes how you approach development constraints because it turns high-end laptops into viable engines for models previously deemed server only without requiring any cloud dependencies or ongoing subscription costs. The boundary of what is possible has moved from expensive hardware requirements to software optimization techniques that allow us to run powerful intelligence on devices we already carry in our pockets every day. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.